All right, ladies and gentlemen, we're diving into 3.2, which is logarithmic functions. So the whole last section we've talked about exponential functions, and today we're going to start relating how exponential and logarithmic functions have a relationship, I guess. We'll just put it that way. So the goals of this section are to recognize and evaluate how logarithmic functions with base A. We're going to look how to graph some log functions. We're going to recognize and evaluate natural log functions, and then we're going to apply to some real-life situations. Now, that's for the whole section. For this video specifically, we are going to learn how to use some key properties of logarithms to evaluate them, and secondly, understand the connection between exponential and logarithmic functions. Now, let's look into it first and foremost. So, if no horizontal line intersects the graph of the function more than once, the function must have a blank. What do you think is behind here? Well, hopefully you remember from our talk about inverses that that's a horizontal line test. If it passed the horizontal line test, it does have an inverse. So the big question that I have for you, think about our exponential functions, right? Our exponential functions, the growth, the decay, we just talked about them. Does an exponential function have an inverse? Go back to the last section or the last video if you need to check. All right? Pause the video. Think about it for a sec. Don't just wait for me to say the answer. Pause the video. So what do you think? What did you come on up with? What do you think is actually happening with these exponential functions? Does it have an inverse? Well, ladies and gentlemen, hopefully that you do understand that it did pass the horizontal line test, all right? It does pass the horizontal line test. It does have an inverse. Do you know what that inverse function is? The inverse function, ladies and gentlemen, is exactly what the topic of conversation is for this lesson in this video, is the logarithmic function. So the exponential function's inverse is the logarithmic function of base A. Interesting stuff, right? So the definition of a log function, all right? Again, we're talking with base A here. Again, we say that x is greater than 0 and that A is greater than 0 but does not equal 1. So don't forget that, okay? The key understanding is that here is our relationship. Here is our inverse in this line right here. This is exactly what the entire point of saying that it did have an inverse was all about. If our function y equals log, the log function, right, with base A of x, if and only if it is true that x is equal to the base A to the exponent y. This only holds true if this holds true, and vice versa. That's what the if and only method goes both ways. So we write that as saying f of x is equal to log with the base A of x. So what are the must-knows? Well, the must-knows are the definition. Y is equal to log of base A of x. X has to equal A to the y. Plain and simple, no ifs, ands, or buts about it. All right. So let's take a look here for a sec. True or false? A logarithmic function is an exponent. What do you think? Is a logarithm an exponent? Yes, yes it is. That's what it is. That's because it is the inverse of the exponential function. It is an exponent. So that's what I want you to think about when evaluating logs. I want you to think, all right, that a logarithm is an exponent specifically. So when you sit there and say, hey, log base A of x, that is the exponent for which A must be raised to obtain x. All right? So let's think about this for a sec. Our first one. F of x is equal to 2 to the x. And we are evaluating, all right, we are evaluating for x being 32. So what this is asking is, hey, f of x is equal to log base 2 of 32. So we want to evaluate this specifically. So log of, and I probably should have put 32 in here. So f of 32. The question is, and I always kind of like to put it off on to the side a little bit here. So that log of 32 equals what, right? 2 to what power equals 32? That's what I think to myself. 2 to what power equals 32? And so that what power, that's the evaluation of your log. Because remember, a logarithm is an exponent. We know that 2 to the 5th is 32. On to this one, f of 2. Once again, you're asking yourself, 4 to what power equals 2? And that's what's going to fill in this question mark area. 2 to what power, or 4, excuse me, to what power gives you a 2? So think about it. How am I going from 4 back down to 2 with an exponent on in there? Well, that's like saying the square root. So it's 4 to the 1/2 power, or the log is evaluated at 1/2. All right, let's keep pushing forward. F of 1 in the example of log base 3 of 1. Once again, 3 to what power gives me 1? That's what I'm asking you. 3 to what power gives me 1? That what power is going to be my answer. Well, how do I get 1 from raising a power in there? Well, the only exponent that gives us a 1 every single time is 0. All right, guys, and let's take a look here at this last one. I challenge you, pause the video right now. See if you can attempt part D before we go on. So f of 1 over 100 is equal to log base 10 of 1 over 100. So you're asking yourself once again, 10 to what power gives me 1 over 100? Well, when you're finishing in a fraction like this, you need to think to yourself a little bit as to what gives me these kind of fractions. What types of exponents give me this type of fraction? Hopefully you remember that some basic rules of exponentials is that the negative exponents will give us this. So 10 to the second is 100, but 10 to the negative second is 1 over 100. All right, ladies and gentlemen. So that's going to wrap it on up for this video here. On our next video, we're going to continue to talk into common logs and some big properties about logarithms.